Today's topic is very interesting because we're going to finally talk about pipe flow, the loss of energy that happens in pipes when fluid is flowing in a pipe, when fluid is moving in a pipe. What are the losses that you can experience? Some of them we call them major energy losses, others are minor energy losses. And all of them, we have a way of analyzing them so that you can determine how much loss you have and so forth. And there are also formulas that are used for analyzing such losses in this kind of flow. So two families, major energy losses and minor energy losses. So here is where this is coming in. We're not saying that we can ignore one group and forget about the other, but all of them are important. If you talk about the major energy losses in pipe flow, the biggest contributor to that is friction as a result of the walls of the pipe. It could be the pipe. Eventually, those pipes become rusty and rough. And even if you are using a new pipe, it may not be smooth all the way. There will always be some debris and some deformities around the periphery of the pipe inside there. So as a result of that, you expect to have friction coming from there. Now here, when you're calculating the losses as a result of friction, the major energy loss, this one comes as a result. I mean, you can use either Darcy's formula or Chase's formula, either of the two. We'll come back to them. So if you talk about this formula, start with Darcy's formula or Darcy-Weisbach formula. The head loss coming from friction is given by HF is equal to 4FLV squared over 2GD. Where, or you can write it as Z, because you can see there's 4 on top and 2 there, or 2FLV squared over GD, because the 2 just cancels with the 4, then you have this one. Now we still need to know what is each of them representing. HF, of course, that is the friction, the loss of head due to friction. F, that's the coefficient of friction. Of course, this one is a function of Reynolds number, where we say H is 0.0791 over Reynolds number raised to power 1 over 4. For 4,000 to that, this is turbulent flow, or H is 16 over Reynolds number for Reynolds number less than 2,000. This is for laminar flow. Now here, L, that is the length of the pipe in meters, V, the velocity of flow, D, that's the diameter of the pipe where the fluid is flowing. Then the same Reynolds number is given by Vd over that nu, then or density times V times D over that, where this one is the velocity. So let's talk about this. Capital V, that's the velocity. This rho, that's our density of the fluid. Then this nu, that's the kinematic viscosity of your fluid. Then we also have D, of course, that's the diameter of the pipe. And the other one is the dynamic viscosity coefficient, mu. Chase's formula, this is another one, where we have pressure difference between P1 and P2 area. So the frictional resistance is FPL V squared, where you can now write it as P1 minus P2A is equal to FPL V squared. The difference in pressure times A gives you the force. F times this product equally gives you the force. And then once you equate them like that, then you can divide through by the specific weight. What you have now is an expression like this, where the specific weight is appearing on both sides. And you can now make HF the subject of the formula, where you say FP LV squared WA. Here we've just picked what is on this other end. That is your HF, and your omega is still there. So In other words, what we are saying is P1 minus P2 over omega. The whole of this is representing the head. So divide through by S so that here you have the loss of head H. So you have F dash P, then LV squared over omega A. That is when you're using Chase's formula, but that's not all. If you make V the subject of the formula, you have omega square root of F, then A over P times HF over L. Now with this one, you can split them. The reason we put this alone is that this omega over F dash, where this one, of course, is referring to that coefficient of friction. This is our C, Chase's constant, which sometimes can even be given, or you are given both values. Then A over P, this is our hydraulic mean depth, or simply R. Then HF over L, that is our loss of head per unit length of the pipe. And then I or S, that's the slope. That's how they come out. Now with this, when you do this, Chase's formula looks this smart. It's simply V equals C MI. That's all. Because everything else has been swallowed up and simplified. So then, where you do that, then you can go ahead and calculate the losses either using Chase's formula or Darcy's formula. Minor losses are many. We have losses due to sudden enlargement, V1 squared minus V2 squared over 2G. Then there's another one. If there's an obstruction in the pipe, rather sudden contraction, the V2 squared over 2G, then 1 over CC, where CC is the coefficient of contraction, minus 1. Then we have, so in general, we're saying HC is K, V squared over 2G, whichever that one is, because K will be representing that value there. Then the third one, the loss of head due to an obstruction in the pipe. It could be the pipe is almost clogged. There's something that is blocking the flow of fluid. For such, it's A, CC, A minus A, then V squared over 2G. The small a you see there is the area of that obstruction, which is the cross-section of area of the object or material which is obstructing the pipe from allowing fluid to flow smoothly. Then A is the cross-section area of your pipe. V is the velocity at which the fluid is flowing. G, of course, that's our acceleration due to gravity. CC, that's the coefficient of contraction. So that constant will definitely be provided. Okay, so there we are, maximum area of obstruction, loss of liquid in pipe. Then loss of head at entrance to the pipe. At entrance to the pipe, sometimes you see leakages, sometimes you see a lot of things. So there's always some loss associated with that. It's given by 0.5 times V squared over 2G. Then loss of head at exit of the pipe, also where the pipe is coming out, because the jet or the water, the liquid will try to enlarge, or it will try to be free as a result of it coming out of that constriction of that confinement in a pipe. So the loss as a result of that is simply V squared over 2G. Then we also have loss of it due to bend in a pipe, which is K V squared over 2G. Again, this is the constant for coefficient of bend. All the minor losses, as you can see, there are quite many, and some of them you can be given one constant value, which will represent them, or you'll be given the values which will guide you to calculating what they are. So pipe fittings can also be able to amount to some loss. Fittings in the pipe. So K V squared over 2G, of course, where K, that is our value coefficient, dependent on what fittings are there, it will also vary. Okay, now let's look at this, using the two formulas, either Chase's or Darcy formula. So here is the pipe, diameter is 350 millimeters. The length of the pipe, 75. and velocity of flow 2.8 meters per second. Then viscosity of the water 0.012 stock, and chase is constant 55. So let's find the head loss due to friction. Using, this is a major loss of head, like we said. So Darcy's formula for chassis. So let's first of all plug the data. D 350 millimeters. So 350 millimeters, if you have to convert it to meters, it becomes 0.35. Then L, that's the length of the pipe, 75 millimeters. Velocity of the pipe is 2.8 meters per second. We've been given chassis constant 55, so our C is 55. Then V, this is our kinematic viscosity, 0.12 stock. When you see this one, we have to convert it. So to convert, we multiply it by 10 to the negative 3. We'll simply divide by 1,000. So then we have 1.2 by 10 to the power negative 6 square meter per second. So the data having been done, we can go now to the first one. Darcy's formula, Darcy-Weisbach formula. So first, here's our Reynolds number. With Reynolds number like that, so here we're saying that Reynolds number is what we need to calculate first. We have VD over nu, so the velocity was 2.8, diameter of the pipe was 0.35, the kinematic viscosity was 1.2 by 10 to the power negative 6. So all this, our answer is 816,666.67. So that's our Reynolds number. Then what else do we have? Looking at the information provided, we also have, just a minute. First of all, we're saying that this Reynolds number is above 4,000, but below that one. That's what we're talking about is this. We are supposed to use the first formula, which is 0.0791 over Reynolds number raised to power 1 over 4. Actually, this is turbulent flow. So 0.0791 over 816,666.67 raised to power that. To get, we just want to find the value for that coefficient of friction. So we have 2.628 by 10 to the negative 3. And with this, we can now go ahead and find our head loss because everything else has been provided except that coefficient of friction, F. So with this, we can now substitute 2 multiplied by this value we've just found times the length of the pipe, which is 78, times the velocity of flow of the liquid, which is 2.8 meters per second, times the diameter of the pipe, which was 0.35, multiplied by gravity, which is 9.81. So then our head loss is simply 0.9 meters. Our head loss is 0.9 meters. We've just used Darcy's formula. The other part was asking us to use Chase's formula. Now with Chase's formula, we need to first of all find the hydraulic mean depth, which is the ratio between area and the perimeter. So the cross-section area is pi d squared over 4 divided by pi d. That's the formula for the perimeter. When you simplify those, number of items are constant. The pi will cancel, the d will cancel partly. You just remain with d over 4. So then d over 4, the diameter of the pipe is 0.35. Divided by 4, you get 0.0875 meters. That is our hydraulic mean depth, M. Then we also have, we can now get back. Here, Chase's constant is 55. Now let's see how we substitute. 2.8 is equal to, because this is our velocity. Velocity is equal to C, then square root of mi, where I is the slope. So here it's like, oh, this information is there, but this one is missing. So making it the subject with this substitution, you'll find that our I will be 0.02962. So we said I is HF over L. The target is this HF. So we can go ahead and make HF the subject, which will now be the product of the length of the pipe by the slope. So 75 times 0.02962, and our answer comes out as in 2.22 meters. That is the loss of head. Now, you can already see that Chase's formula is usually useful when you're just trying to make an estimate, because even the value is smaller despite the other one giving us a bigger number, showing that here, if you want to get something even more and more accurate, you may go for the other one. Even when you want to design or to come up with such pipe flow, with this, there could be some assumptions that you may get rid of. But here, this is our final answer using Chase's formula. Now, here is another one. Here we have horizontal pipeline. Fluid is flowing at the rate of 0.05 cubic meters per second. We need to find the loss of head due to an abrupt expansion or the pressure difference in the two pipes. Okay, let's plant the data according to the question. Of course, also the change in pressure due to sudden without any loss. Okay. Diameter 1 is 0.15 because it's 150 millimeters. Meaning area 1 by d squared over 4 is 0.01767. Then diameter 2 is 0.225 meters. Meaning that the area coming from there is 0.03976. Then we also have the discharge is 0.05 cubic meters per second. Seems we're now ready to get to the first part. So the discharge having been A1, V1 is A2, V2 means we can find velocity 1. Velocity 1, we make velocity 1 the subject, it's discharge over area. So the discharge divided by our area, you get 2.83 meters per second. Velocity 2 is discharge over area 2, which gives us 1.258 meters per second. Again, with this, we can now find the head loss due to sudden enlargement. We said is V1 minus V2 squared over 2G. So we plug the formulas inside, the two values inside, 2.83 minus 1.258, everything squared over 2 by 9.81. So due to that enlargement, we have 0.126 as our loss. So 0.126 meters, that's our head loss. Then let's apply Bernoulli's equation. This is the horizontal pipe. So Z1, Z2, they are out. We can cancel them out. Then we include that head sudden loss in the loss due to sudden enlargement. So with this, we can just go ahead and rearrange the formula, P1 minus P2 over omega, then that one. Now, we want the pressure difference, which is P2 minus P1. So with this, actually what we're looking for is this P2 minus P1 over omega. So there, whatever we find is 0.202 meters of water. Here we've just planted everything we have here, and we have our answer, 0.202 meters of water. Change in pressure with gradual change with no loss. So here, it's like we rewrite Bernoulli's equation without including the loss of head. We rewrite that equation, but we don't put HE. And we go ahead and do the same calculation. So with this, making P1 minus P2 over omega the subject, we have P1 minus P2 over omega, and our answer is 0.328 meters of water. Now, here's the thing. When you ignore the losses, look at what we have. The change in pressure is high. Here, when we don't ignore, the change in pressure is quite low, which is very much expected because the other one is the real part of the knowledge equation. The other one is in the theoretical part. Okay, then here's our exercise. You can take your time, go through and see how the whole experience comes out. Feel free to post the comments where you feel there's something that you need to clarify, and I'll quickly get back.